Hey, hi, welcome to the session on Prelude to pointers. So, in this session, we will be taking a look at the following. So, the agenda is as follows. We'll be talking about pointers. We'll be getting introduced to concept around pointers. So, we'll see the basics of memory and what is an address. Basically, in this presentation, we'll see how C code gets translated into the executable format, and we'll also see a sample outlay of executable. These are required for you to later understand the concept of addresses and operators in extra. So that's why this is like a prelude to pointers. It's just basic knowledge that you need to know to understand pointers better. Just the pointer itself is the difficult topic per se. So pay attention. The road ahead is full of landmine. So pay attention, read the same material again and again, do the exercises. The concepts will become clear, and the real fun in C starts from now on. So, if you take a typical program, finally, what is a program? A program is a sequence of instructions. What a CPU does is it executes a sequence of instruction. So the program consists of two parts. It's a sequence of instructions and the data associated with it. Right, there are two parts of it. You basically the computer executes one instruction, or the processor executes a sequence of instructions, and each instruction manipulates some data, and the data is either present in the data memory where the data is stored for the program, or the data is present in the CPU registers. So that's what, as simple as one thing could say, a CPU does. It just executes instruction. Each instruction does some operation, and each instruction does some operation, and each instruction does some operation on data, and the data can exist either in the data memory or registers. So let's take an example that of what's shown here. What's shown here is a hypothetical program in hypothetical language. So in this case, you see the blue bar. This blue bar is where the current instruction executed by the processor. So it's also called PC. It stands for program counter. So that indicates what is the current instruction that is getting executed by the processor. So the current instruction that is executing by the processor is move R2 to 1000. So as a result of this execution of this instruction, the register R2 becomes 1000, and that's what you would see here. When that instruction is executed, the CPU assigns the value of a register R2 to 1000, and then next instruction is load word. So load word is like it's an instruction that reads from memory and then writes into register. So in this case, load word R2, the value in R2 is 1000. So this instruction tells the processor to read from the location 1000 and write it to R0. So because R2 is 1000, so reads from the location 1000, and at the location 1000 value of 100 exists. So basically, after the instruction is executed, R0 will become 100. You can see that R0 becomes 100. Next instruction is just cooked up instruction. You are reading from the location of R2 plus 1. R2 is currently 1000. 1000 plus 1 will be 1001. And you are writing into register R1. And R1 will become 200 because location 1001 contains 200. The next instruction the processor executes is a min. It's again a cooked up instruction just for your knowledge. So in the min instruction is R0, R1. So the value of R0 currently is 100 and the value of R1 is 200. The minimum of this again is 100. So after the end of this instruction, R0 will become R0 will become 100, as you see this, right? So R0 has become 100 because R0 has become 100 too. Now, so at the end of this instruction, what really happens is R0 has become 100, and then the next instruction is store word. Like load word is reading from memory, store word is storing back into memory. So you're storing back to the address 1002 the value of R0. R0 currently is 100. So when after this instruction is executed, the location 1002 will become 100. Right? So this is what a processor does. A processor executes an instruction, one instruction after the other, and the instruction typically consists of reading from memory, writing from memory, doing some mathematical operation. So a sequence of instruction forms a program, the corresponding data is loaded into data memory, right? So if you typically take what I've shown here is we're seeing read instructions, write instructions, and some math operation. Like for example, load is a read instruction, store is a write instruction, and min in our case is some kind of math operation. And each instruction resides in a memory address. So each instruction resides, like for example, at I can say that address 2000, the instruction load word exists, right? So the instructions themselves reside at a memory location. Similarly, the data also resides at a memory location. And you can see that the instruction accesses the data memory, like load word R1, R2, right? This instruction was accessing the location 1000 and writing it to register R0. So that's all a program is. It's just a sequence of instructions. And instruction can either be read, write, memory operations, math operations, and many more such categories. Right? Now, this all of you would know. So let me go ahead and go to the next one. So all of you would know this, that here is a program. Right? So here is a program. And this is a program that your processor is executing. It has a data memory also here, sitting over here. And this is the assembly instruction corresponding to the program, and this is the memory where the data exists. In the program memory, your code is running. In the data memory, your data is present. And what we do actually is that we also have the C program. So somehow a C program is what you understand, what you as a programmer can logically think in a higher level language. And this assembly program is what the computer understands or what a processor understands. So essentially somebody has to translate from the C program that you write and translate into assembly. Like for example, that is the job of a compiler. So what the compiler actually does is it translates C to assembly. So in this case, the compiler has taken this program and created an executable file. An executable file is a file that contains assembly instructions and also the corresponding data. So what the compiler in this case has done is taken the simple program and has converted into this assembly level language. So what it did is, like, let's take x equals 1. So this particular, for C code has been converted into these three assembly statements. In this case, it's pretty simple. Let's take, for example, int x equals 100 is there. So the compiler has created an executable file in which it's placed the variable x at address 5000. So essentially, the compiler has assigned the variable x, the address of 1000. So what it means is that whenever you are reading the value, you will be reading from the address 5000. Whenever reading the value of x, you will be reading the memory location 5000. Whenever writing to it, you'll be writing into memory location 5000. So that's what the compiler is doing. It assigns this global variable some address. It assigns this function also some address. This function now f1 is present at the address 1000, and each of the C statements it produces a corresponding assembly code. So in this case, it's very simple: x equals x plus 1. Now the compiler knows, and this is just a hypothetical understanding. I just simplified. There are much more intricacies. There are just to understand what the compiler does. So in this case, the compiler knows that here variable x is at address 5000, right? So x equals x plus 1 means I should read the address 5000, increment by 1, and then write it back to address 5000. So that's what this is doing. If we take a look at this instruction, R0 is 5000, R1 equals R0 plus 1, which means read the location 5000, add 1, and write it to memory location R1. That's the second instruction. And third instruction is whatever is the value of R1, write to memory location that R0 contains. So R0 contains 5000, right? So you can see that the compiler has produced for these two C statements 3 assembly statements. One is reading from the memory location, incrementing the value, and the next second one is writing back to the memory location. So that's the job of the compiler. It converts C code into assembly code. It assigns global variables addresses. It assigns functions addresses, and it does many more things, but it creates an assembly equivalent of the C code. So once that is done, what happens next is there is something called a loader. So this actually sits in some executable file. So this is how an executable file actually looks. If you take a look at the executable file, inside it there will be sequence of addresses and value, right? So at the address 1000, this is the binary value that will be stored. At address 1000, this is the binary value that will be stored. At address 1002, this is the binary value that we stored. So this binary value of 100100, what is the value, corresponds to this instruction, the first instruction. Just give me a second. So this is called the binary file. So basically what this contains is all the assembly instructions corresponding to the C code and the addresses in which they set upon. And each assembly instruction, like address, this assembly instruction is what you understand as a programmer understands, right? But processor, everything is ones and zeros only. So this is the correspond. This is called the opcode of this instruction. So the binary file contains a pair of address and value. That's all it contains, a pair of address and its value. Similarly, on the data side, you can see that address location 5000, the initial value of the variable is 100, right? So initial value of the variable is 100 means before coming to the main program, before main is executed, the variable x needs to be made 100, right? You can assume that when you enter main, the value of x will be 100. So somehow magically that has to be done because C program only starts when the main starts, right? So what you do is that you go ahead and say somehow, hey, this x, right? This x has a value 100 and it's stored inside this file, executable file. Now what the loader does it copies the content of this file into the processor memory. So for example, address 1000, it copies the first instruction. Address 1001, the next instruction. Address 1002, the next instruction. Basically, it reads this executable file and writes into the program memory and data memory, right? And so here you have written the data memory is 5000 and its value must be 100. That's what the file contains. So what the loader will do is that it will say, oh, this is data memory. It has a value of 100. So let me go ahead and in the processor's memory somehow write at location 5000 the value of 100. So by doing this, if the program goes to main now, the location 5000, which corresponds to global variable x, will have the value of 100, right? So the compiler, what it does is that it translates x into a memory location. It specifies as though the variable x resides at the location 5000. It also says in the executable file, hey loader, the location 5000 must be initialized to the value of 100. Right? And when the loader reads this file, it understands that, hey, this is the assembly instruction, this is the code region. So in the program memory at address 1000, I need to fill the first instruction. So it reads this, transfers it to program memory, it reads this section, transfers into data memory, and starts executing the program. Right? So this is the basics, as in before main. This is the basic, as in compiler converts C code into assembly code. It assigns global variables addresses. It also specifies the initial value of global variables. See, it assigns address 5000. It specifies the initial value of the global variable also. So in the executable file. So that's what the compiler does. It produces an executable file which has assembly instruction, which has addresses for global variables. It has addresses for functions. It also has initial value of global variables. And all these things are stored as binary. Right? And what the loader does is that loader copies this content into the executable. Loader is an element which reads this file and transfers the content into program and data memory appropriately. And then the loader will say start executing the program. So this is the overall workflow of how from C program you go into executable. And this is a very simplified version. There are a lot of complexities involved, but you can get the overall idea, right? This is how it works. Okay, so next one is so what does an object file look like? So there are two parts to it which you're going to talk about. One is called the object file and one is called the executable file. Now, like I said, the object file consists of opcodes. So these are this is the assembly which you understand, mnemonic, and this is the corresponding opcode. So this is the object file produced by the compiler. Now it looks something like this. The compiler has something called sections. .text section means it contains all the assembly instruction. dot data section here that you can see here. Yeah, dot data section that you see here, which means that this section contains all the global variables and their initial value. So this is just a convention. The dot text contains all the assembly instructions. Dot data contains all the global variables and their initial value. And this is the executable file produced by the compiler. Now see that these addresses initially are assigned 0. They're not actually assigned any addresses. So this is our relative addresses. The compiler itself does not know where, at what address should the main program go. It has no idea. It has no such idea. So who has that idea? So the idea is provided by something called linker command file. So linker command file is specific to a processor or specific to a board. So in this board, the linker command file, the dot text section begins at address 500 and dot data section begins at address 100, right? So the dot text section begins at address 500, dot data section begins at address 100. For a different processor, dot text might begin at address 2000 and dot data might begin at 5000, right? So this linker command file is specific to a board or is specific to a processor. So linker command file says where these sections should finally reside in the executable, right? So that's what happens. So when you mix these together, a final executable is actually produced. And this is the final executable. As you can see that the final executable contains fully resolved addresses. The final executable contains fully resolved addresses. Dot text begins at address 5000, data begins at address 100, right? So that's done by the compiler. The compiler actually, not the compiler, linker. It puts the dot text section and creates a new file called executable file called which contains assembly instructions and the data what is the initial value of memory in the data section, but addresses are resolved. You know exactly know that this function f1 or main, it begins at address 500. So because this fellow, the linker command file specifies where all your code should reside, where all your data should reside. Okay, so this is very fundamental. I would say few things to note. This executable is in binary format. So what binary format actually means is that everybody talks about binary. Finally everything in a file, you take a file, finally everything is nothing but it's an 8-bit character, right? Finally is nothing but an 8-bit character. Why it's called binary? Because if you, for example, if you take this opcode and it's stored inside the file, every file, if you take a text and you try to interpret this, let's take this opcode and you try to interpret this as ASCII characters. So you have to take 8 bits from here, right? So these 8 bits might say, for example, have a ASCII value of 223. Now when you're trying to open as a text file, the editor might say, hey, 223 is a control character, or it does not have an equivalent ASCII character. So it will start printing garbage. So that's why it's called a binary file. Binary file means it contains bytes whose ASCII value are not printable, or it contains characters whose ASCII value are not printable. So that's why it's called a binary format. So if you open a binary file via VI or any editor, every editor is going to read the file byte by byte. It'll read first byte, second byte, and each byte it'll try to find out what is the character corresponding to it. But the byte value may not have a corresponding character, right? It might be some control character or it might be non-displayable character. So that's why it's called a binary file. So executable is in a binary format because it just contains ones and zeros, and it's not meant to store character values. It's not meant to store A, B, C, D, E, F, G, H. It is just combination of address and opcode. So for in this case, like I said, if you take this opcode and try to interpret byte wise, the value of the first 1 byte might be 123 or 223, and sorry, not 223 is not even possible, sorry, because it's outside the ASCII range. So let's say value comes to 118. If it's 118, it means that, hey, it's a binary file that doesn't have character, it does not have any ASCII. So the VI editor will actually fill, or the editor that you're trying to open this file with will start filling blank characters, or we'll start putting garbage. Okay, so that's why executable is in binary format. One can see the executable as, logically one can see the executable as, if there is an address and a value. An executable file is nothing but address and a value. There are a lot of other information. I'm not getting into it, but that's what an executable file contains. A loader will look into this file and load into program memory, right? And in the executable file, for every global variable and every function, for every global variable, the final address and value would be known. Like for example, the address X is now located at address 1000, and the initial value is also present. So the address at which the final global variables are going to be placed is known in the sense that if you take a look at the executable file and try to open it, try to read from it, you will get the address of the global variables as well as the value inside. Okay. So that's the anatomy of the executable file. Okay. So that's how executable file is. So what we saw was, just a summary, compiler converts C code into object in executable file. The executable file contains assembly instructions for a processor and the initial value of global variables and its address. Executable file, in the code section, all the assembly instructions are placed. In the data sections, all the data memory is placed, all the data, initial data. And the data, as far as C code is concerned, is nothing but the global variables, initially at least. So global variables, there are three kinds of data you would know and see, that there is a global variable, there is a stack, and there is a heap. And we'll see what and how it is modeled later. There is something called runtime model, we'll see that later. But the data is, that is what the data, the initial data for now is you can assume that it's a global variable. Executable is in binary format, we saw that. Executable can be viewed as address data pair. Loader loads from the program memory into data, from the executable file into data, into the processor loader moves. And every global variable, I would say every variable, it's a very loosely thing, but as far as you're concerned right now, you can assume that every global variable, every function is assigned an address when the final executable is created. Okay. So all the global variables and the addresses that they reside and the initial value is the data is present in the final executable. Okay, that's it for the first session. Thank you.